Anyway, one of the things that came up is the question as to whether or not quantum events occur when the collapse of the wave packet occurs. I think that's getting the causality the wrong way around. Rather, it's the quantum event that causes the collapse of the wave function, because the wave function is simply our encoding in the theory of what the state of what the world is all about at the present moment. And when our knowledge of the world changes, then of course the wave function changes. Of course, the wave function is not does not always encode that. There are situations which, especially Aharonov was most important in describing, in which one can place conditions both before and after, which cannot even be encoded by a wave function. And this illustrates it can be encoded then by something like the two-time formalism of Aharonov or the decoherence functional formalism that Hartle and Gell-Mann developed. It illustrates once again that the wave function isn't something that sits there and does things like collapse. What I'm going to talk about today is, in a sense, going to be a paraphrase of John Wheeler's dictum: no quantum event is an event unless it is a measured event, or unless it is an observed event. What I want to talk about in particular is some work that I did with Jonathan Oppenheim, and we and Benny Resnick and various other people in Aharonov's group published some papers back a few years ago. And the question is, when does an event occur? And in particular, the very simplest question: I have a free particle which is traveling along, and I want to know, when does it hit the point x equals 0? I want to record the time at which it gets to the point x equals 0. Now, classically, one could just say this is just x, the initial position, divided by the velocity. But quantum particles have wave packets and so forth. They don't really have an initial position. They don't really have a well-defined velocity, etc. And besides, what I want to know is, when does it get there? So I have to have some way of recording that the particle arrived at x equals 0. Is there some operator t which defines the time for the particle? Well, this is, of course, well known to not exist. Pauli already showed this. If it were true, then the time derivative of this function, of this operator, would have to be equal to 1, i.e. it would commute with the Hamiltonian and give it equal to I. That means that it's a Hamiltonian, t is a Hamiltonian translation operator, which would then mean that the spectrum would have to go from minus infinity to infinity for the Hamiltonian. And most Hamiltonians don't have that feature. Thus, the measurement of the time of an event is not a measurement of some operator directly defined with respect to that event. In quantum field theory, of course, this is also true of even space. The things that are measurable there are the values of the field occurring at some space-time point, and one then has to reinterpret those in terms of particles and decide when the particle has arrived, let's say, at x equals 0. So, how do we measure it? We have to generate a clock. What is a clock? Clock is something which is a dynamic object which has a pointer on it, and by reading the position of that pointer, we can figure out what the time the clock shows. This, of course, depends on the clock being put in a very particular state, or a whole class of states, I should say. Because after all, if I take my watch, I put it on the floor, and I bash it with a hammer, that's a perfectly good state for the clock, but it doesn't operate as a time measuring device very well. In particular, this pointer had better obey something like that same equation. The time derivative of p is equal to 1. Obviously, it cannot always do that, but in certain situations and for certain states of the clock, it can at least be approximately true. For example, if my Hamiltonian is p squared over 2m, a free particle, pi squared over 2m, a free particle, then if I concentrate the initial wave packet near pi equals m times v naught, then the position of that particle divided by that v naught, that average value of v naught, is going to approximately give me a good, reasonable definition of time. However, this clock cannot be arbitrarily accurate, because what happens is that if one looks at the commutator of the pointer with the Hamiltonian, that's approximately equal to 1. If that tells us that there's an uncertainty relationship between the pointer and the Hamiltonian. The more accurate I make the clock, the smaller I make the uncertainty in delta p, the larger the uncertainty in the Hamiltonian of the clock has to become. So I've got a limitation on the ability to measure by the Hamiltonian of the clock itself. Of course, at first you would say, what's this got to do with the particle? I want to know when the particle arrives at the point x equals 0. And the fact that my clock has got this highly uncertain Hamiltonian, who cares? Well, the reason that you have to care is because you have to couple the particle to the clock. You have to figure out some way of, for example, stopping the clock or starting the clock at the point at which that particle comes and hits x equals 0. Notice that this is the famous Heisenberg time-energy uncertainty relation, which has had a huge, massive, long history of misunderstandings, etc., by many, many people. One of the most famous was the Bohr-Einstein weighing of energy debate, where Bohr seemed to imply that the only way in which quantum mechanics can be consistent is if general relativity is true. Now, that would have been an astonishing conclusion if it was correct. Einstein should have been extremely happy. He wasn't. And with good reason, because the fundamental assumption that Bohr made was that the energy inside the clock had weight, and any theory in which energy has weight, not just general relativity, immediately leads to the same conclusions that Bohr came to. So clocks can't be arbitrarily accurate. In order to figure out whether the particle arrives at x equals 0, one has to couple that clock to the particle. For example, one has to switch on the clock. What do I mean by switch on the clock? I mean that beforehand, the Hamiltonian of the clock is 0. The pointer simply sits pointing at 0, let us say. And when the particle arrives, suddenly this clock starts to tick. Then afterwards, you can measure the clock. You know what time you measured the clock, and you can then tell what time the particle arrived at x equals 0. But of course, that function, that coupling function between the particle and the clock, which will look something like this, where theta is the usual Heaviside theta function, x is the position of the particle, h is the Hamiltonian of the clock. If I set up the whole Hamiltonian like this, then when the particle arrives at x equals 0, it switches on the clock and this clock starts to tick. But the clock is uncertain in energy. Therefore, that second term, which the particle sees as a potential, looks like if the energy of the clock were exactly equal to its actual average energy, it wouldn't do anything, but then, of course, the clock wouldn't tick. The more accurate the clock is, the bigger the variable step function that the particle has to run into. And in particular, whether that step function is positive or negative, once that step function becomes of the same order as the energy of the clock, the particle is simply going to bounce off the potential. The particle will, according to our calculation, arrive at x equals 0, see this huge potential, and just bounce right back, and the clock will never start ticking. I.e., as far as our measurement of the clock arriving at x equals 0, the particle never arrives. So the very attempt to measure whether or not the particle has arrived stops the particle from ever arriving. This tells us that the accuracy with which one has to design the clock has to be finite. In fact, one gets basically an uncertainty relationship between the clock, between the arrival time, which I've again designated by capital T, and the energy of the particle itself. Not the energy of the clock, but the energy of the particle. That if the energy if the accuracy of the clock is too large, the clock simply stops the particle from ever arriving. Now one can say, well, perhaps one can fix this. One can, for example, put in a little potential just beforehand. One can put a little accelerator that accelerates the particle or something like this. And we did analyses of a whole bunch of these kinds of situations and showed that they, in fact, don't help. That the very presence of measuring whether or not this event occurs stops the event from occurring. This is very different from the usual time-energy uncertainty relationship, which is a relationship between the energy of a body and how well any pointer within the body can actually measure the time. It's a relationship in which the time, as indicated by the pointer of the clock, and the this is a relationship between the accuracy of the clock and the energy of the system is that one is trying to measure the time of. Producing a real proof of this is difficult. One can sort of produce a somewhat slightly hand-waving proof of this in another situation in which one is trying to measure the time of traversal. One has 2 points, and one wants to ask how long does the particle take to traverse that distance between those 2 points. The thing is that the measurement of that traversal time is also a measurement of the momentum of the particle. Right? If I know I've got a certain distance L, and I know how long it took the particle to traverse that distance L, then I know what its velocity and what its momentum is. What that means, and I also know where this occurs, namely more or less the midpoint plus or minus L is where the particle was when that traversal time was measured. If one could measure the traversal time with a higher accuracy than this delta T times energy of the particle, one could then measure both the momentum and the position of the particle to better than the Heisenberg uncertainty relationship. So that suggests that this uncertainty, clock accuracy, energy of the particle uncertainty is much more generic than just the simple example we looked at. One of the things that one could ask is, for example, well, let me define the time of arrival by estimating when it's going to get there. I'm not going to care whether it actually gets there or not, but I'm going to estimate it by dividing, now as an operator equation, x divided by p. The problem, of course, is that p, the momentum, is an operator which has a 0, so its inverse is undefined. And if we want to try and make an operator for which this is more well-defined, we can, for example, going into Fourier transform space, replace that 1 over the square root of k by 1 over the square root of some function of k, which goes to 0. So f of k goes, I've got this the wrong way around. F of k is supposed to be k for large k and epsilon squared over k for very small k. So epsilon squared over k obviously has 1 over that has a well-defined limit as k goes to 0. So this operator would then become a well-defined operator. And as long as my particle didn't have very small momenta, that would seem to be a reasonable estimate. Well, what happens if we use this operator to actually measure the time of arrival? And we discover that the time of arrival is 0. At that point, consistently, one would assume that the particle at that point is sitting at x equals 0, right? This operator has told me that it's arrived right now at x equals 0, so that's where it must be. If one looks at the eigenvalues of these operators, one has to do a certain regularization because these are not well-defined square integrable eigenvalues. But if one looks at the eigenvalues, one finds that the particle only has a probability of about 50% of actually being at x equals 0. It's got a probability of being 50% being exponentially far away from x equals 0. So is that a good time of arrival operator if half the time the particle is nowhere near where it says it was when it arrived? I want to give some speculative things about quantum gravity related to this. I published this in a Canadian Journal of Physics, and I sent in the title, Why Study Quantum Gravity? And when the paper came out, the title said, Why Study Quantum Theory? So this is a question of, can one measure the metric? Now, what do I mean by that? I've got two things. I want to measure the distance between them. Can I measure the distance between them? Well, in order to measure the distance between them, I've got to stick a ruler between them to measure the distance between them. But in order to measure that distance between them, the relative momenta of the two particles has got to be uncertain by Heisenberg's uncertainty relationship. What causes that uncertainty? Well, of course, sticking my ruler in there, the endpoints of the ruler are going to apply stresses to the thing that I'm trying to measure. In order to measure the distance between two particles, there's got to be some stresses in the ruler as I stick it in there. So that tells me that delta P is going to be related to the stress of the ruler itself. Delta L, or L, the length of the ruler, is proportional to the distance between those two objects, which has got an uncertainty delta x. So delta L has got an uncertainty in the metric. That delta x, where's my pointer? That delta x is not the uncertainty in x, but the distance between the 2 points in coordinate space. The uncertainty in the length of the ruler is then going to be given by the uncertainty in the metric times this stuff. When I multiply these guys together, this delta L, delta P now gives me an uncertainty relationship which says that delta GXX times delta of capital GXX times the 4 volume over which that measurement is being taken place must be greater than or equal to 1. So this kind of a very crude uncertainty analysis of the measurement of metrics, etc., seems to suggest that quantum mechanics should have some sort of an uncertainty relationship, not between the metric and components of the Christoffel symbols, the connection, but an uncertainty, which is what the usual thing is. The connection has time derivatives of the metric in it. But this is a connection, an uncertainty relationship between the metric and the curvature of space-time. Now, no quantum theory that I know of has uncertainty relationships like this. But it might suggest that perhaps it should, and we should be looking for something which is going to give this to us. This is very much like the Heisenberg microscope Bohr, which Bohr criticized very strongly. And one last note that I want to give you, which is just a realization, and a lot of you have probably had this realization long ago. LIGO is really the world's biggest Heisenberg microscope. This is the sensitivity curve for advanced LIGO, the design sensitivity curve for advanced LIGO. And if we look at the thing that completely dominates the noise, it's quantum. It arises from exactly the same origin as the uncertainty did in the Heisenberg microscope, namely uncertainty in the forces on the mirrors due to shot noise on the mirrors versus uncertainty in the observation due to shot noise in the observations that are coming out of the LIGO detector. This is not an electron. This is a 40-kilogram lump of quartz that is being measured right now today to the quantum limit. These uncertainty relationships that one always plays around with are really there in the macroscopic world. And I suspect very strongly that a proper analysis of this would show that this already disproves Penrose's conjectures about gravitational decoherence. And I'm done.
Thanks, Bill. That was terrific.